Hello and welcome to this video where today we're looking at electric potential. And when we looked at gravitational fields, we saw that the gravitational potential was related to the energy that an object has inside a gravitational field. For electric potential, it's basically exactly the same. It's related to the amount of energy that an object has inside an electric field. So if we think about this just for a second, let's imagine we've got a positive charge over here that's fixed and we want to move this positive charge towards it. Well, we have to do some work. I would have to actually push on this to move it towards it. So I'm putting some work into this, which becomes the electric potential for this object. If I then let it go, it would then move backwards. So that electric potential would then be converted into kinetic energy and it would accelerate and it would move in this direction away from this thing because they're both positive, so they repel. So in order to move a charge in an electric field, we have to do some work. And the electric potential we can define like this. So the electric potential of a certain point in the field is defined like this. It is the electric potential energy that a positive unit charge, in other words 1 coulomb, so when we say unit charge we're saying plus because it's positive 1 coulomb, that charge would have at that point in the field. So if this is a 1 coulomb charge and it has a certain amount of electric potential energy at this point, then because it is a unit charge, then the electric potential is the same as the electric potential energy that this object's got. Now we can calculate this in exactly the same way that we did with gravitational fields. So again, here's our definition, and it depends upon two things. It depends upon the charge of the object that's actually creating the electric field, so that's Q, and it depends upon the distance away from that particular object. Now distance is measured in meters and charge is measured in coulombs. So this is the electric potential and that's measured in coulombs per meter. Coulombs per meter also coincidentally are exactly the same units as volts. So electric potential is actually measured in volts. Now we can make this equation simpler because we know that this whole thing here, the 1 over 4 pi epsilon naught, is a nice easy number to remember. It's 9 times 10 to the 9. So our equation for electric potential simply becomes this here. Now in the same way that we looked at a graph for gravitational potential, we can do the same for electric potential. It's slightly more complicated because we've got two different things going on. If we have a repulsive force, so if we have, for example, this is our positive charge that's creating our electric field, and we put a small positive charge over here, these two will repel each other. So this one will be repelled away from here because it's much smaller, so we'll assume this one doesn't move. So we've got a repulsive force. If, however, we put a negative charge here, then obviously this will be attracted in this direction. So we've got an attraction or a repulsion one. So it's slightly more complicated than gravitational fields. So if we look at this equation, if the thing that that is creating the electric field is positive, then our electric potential will be positive. However, if we have a charge that's negative, that's creating our electric field, then the potential will be negative. So we've got kind of two different graphs. So this is if we've got a repulsive force between our two objects, but well, between our positive chest charge and the thing that's creating our electric potential. In other words, if we have a positive charge that's creating the electric field, we have a graph that looks like this. So the electric potential is always positive. If, however, we have the charge that's creating the electric field to be negative, then it looks like this. They're exactly the same. This curve is reflected simply in the x-axis. It's just so this is basically for a negative charge creating the field, and this is for a positive one. So that's something you need to be aware of. So you could, for example, be asked to draw the graph for the electric potential for a positive charge or for a negative charge, or I suppose perhaps for both. So we've got an equation, so let's do a really quick example. So we've got a positive charge, it's placed a certain distance from a sphere, and this sphere has a positive charge given by this charge over here. The positive charge is repelled from the sphere by this much, so we want to know how much the potential has changed whilst this is going on. So we've got this equation here. So basically what we do is if we want the change in potential, that will be the final potential minus the initial potential. So if we just put our numbers in, the final potential, well, we've got our thing over here. It was here, it's moved over here. So our final potential is going to be related to the distance that it moved to. So our final potential will be equal to our constant, 9 times 10 to the 9, multiplied by the charge of the thing that's actually creating the electric field. Well, that's the charge on this, so in other words, it's plus 2.9 microcoulombs, so 2.9 times 10 to the minus, times 10 to the minus 6 coulombs, divided by the distance. Well, the distance is the distance it started at, which was 0.04 meters, plus the extra distance it's moved, so it's repelled by another 25 centimeters, so in other words, another 0.25 meters, like that. So that's our potential, our final potential. We also want to take away the starting potential, because we want to, if you look, we want the change in the potential experienced by this charge. So again, we just put our numbers in. So we've got 9 times 10 to the 9 multiplied by the charge that's creating the electric field, 2.9 times 10 to the minus 6, divided by the starting distance. Well, the starting distance was just 0.04. So if we do that on our calculator, we end up with 90,000 minus 652,500. And so we end up with minus 5.6 times 10 to the 5 volts. Alternatively, coulombs per meter if you want to write it in that way. So the potential changed by minus 5.6 times 10 to the 5 volts. Okay, so that's an example of the type of question you can be asked. Now, again, comparing electric fields to gravitational fields, we saw that if you had a graph of the potential and you worked out what the gradient was, then it told you what the gravitational potential was. This is exactly the same. If you have a graph like this and you calculate a gradient at a point on this graph, then it will tell you what the electric field strength is at that point. So before we had gravitational field strength was equal to basically that, so the change in potential divided by the change in distance, in other words the gradient, gave you the gravitational field strength. This time it's exactly the same, apart from it gives you the electric field strength. So again, if you're given a graph like this, then if you work out the gradient, it will tell you what the electric field strength is at that particular point. And you can see that as you move along, the electric field strength actually changes. So it's strongest here because the gradient's biggest, and the electric field strength gets smaller and smaller as you go along because the gradient gradually goes to 0. So again, that's something that you just need to be aware of. So finally, we kind of alluded to this before where we looked at the change in potential. Electric potential difference is very important, especially when we come to look at capacitors, because we'll be looking at the potential difference between two plates. So electric potential difference, again, we can define. It's the energy that's needed to move a certain charge in an electric field, because as we saw before, you have to do some work, so you have to put some energy in if you want to push a positive charge towards another positive charge, or you can kind of get work out, so the electric field does work on a charge if it repels it and it moves it away. So to calculate the electric potential difference, you just want to know the energy that's needed to move this charge. So it's given by this equation. This is your change in potential. So that's the change in potential. So that's measured in volts. Q is the charge of the object that's in this electric field now. So rather than the charge actually creating the electric field, it's the charge of the object, and that's measured in coulombs. And then this is simply the work done, which is basically the energy that's transferred, so that's measured in joules. So the work done is simply the charge of your object in that electric field multiplied by the change of potential that it sees. So for example, we want to have a look, see how much work is done to move an electron through a potential difference of 2000 volts. So it's starting over here, you've got an electron here, you want to move it to here, but in doing so you've got to move it, the potential difference between there and there is 2000 volts. Okay, so we simply just use this equation. So the work done is simply the charge of our object? Well, it's an electron, so it's got a charge of 1.6 times 10 to the minus 19 coulombs, multiplied by the potential difference, which is 2000. And if you do that, you get 3.2 times 10 to the minus 16 joules. In actual fact, you've really met this before, because when you studied Unit 1 and Unit 2, you defined an electron volt, which was the work done to move an electron through 1 volt or through 1 volt of potential difference. So this equation you've actually seen before. So finally, we just want to have a look at equipotentials, because in the same way that we did with gravitational fields, we can draw lines that show us constant potential. And again, we've got a radial field and we've got a uniform field, and we see exactly the same sort of patterns that we did for gravitational fields. So for example, for a radial field, we can see that they form concentric circles around a charge. So we've got circles, and what we'll see is that if the difference between each of these potentials, so let's imagine that the difference between this potential and this potential was 1 volt, and the difference between that one and that one was 1 volt, and so on, that as we get further and further away from this charge, then the distance of these equipotentials gets bigger and bigger and bigger. So the actual potential difference between there and there is 1 volt, and between there and there is 1 volt, but the distance that you have to move in order to see a potential difference of 1 volt gets bigger and bigger and bigger. And again, just like gravitational fields, the reason for that is because for a radial field, the electric field strength is stronger here, and so you only have to move a small amount of distance to see a change in potential, whereas out here you have to move a lot further to see the same potential difference. So that's a radial field. For a uniform field, it's actually much simpler. So here we've got a potential difference of 5,000 volts, and these equipotentials are nice straight lines. And what you see is that they're all equally spaced. So here, for example, we can see that we've got 1, 2, 3, 4 equipotentials. So each of these is a distance, is a potential of 1. So this one's at a potential of 1,000 volts. This one's a potential of 2,000 volts, and 3,000 volts, and 4,000 volts, and 5,000 volts. So if you have, for example, a potential of 5,000 volts and 0 volts, if you're asked to draw equipotential of 2,500 volts, it's just exactly halfway in between. So these fields are easy to draw. These are a bit more tricky. One of the important things to realize is that equipotentials and field lines are always at 90 degrees to each other. So if you draw the electric field lines for this, then they go in this direction, they'll go downwards, and they're perpendicular to the equipotentials in exactly the same way that if you draw the field lines on this, you'll get that kind of spoke kind of thing, like spokes on a bicycle wheel. But again, the field lines and the equipotentials are always at 90 degrees to each other. The final kind of thing to say is that the values of these equipotentials will obviously be different if you have a positive charge creating your electric field, or if you've got a negative charge. These will be positive if you have a positive charge, but they will obviously be negative if you have a negative charge. That simply comes from, if you go back and look at the formula for potential, it's equal to our constant times Q over R. So if you have a negative charge creating an electric field, potential is negative, and so therefore all of your equipotentials will have a negative number. If you have a positive charge, your potentials are all positive, and so these will be positive too. Okay, so that brings us to the end of our video on electric potential. Thank you very much for watching, and I'll see you again soon.